Great. So thanks, Andrew, for that beautiful talk. And we're going to go a bit higher level with this to talk about remote sensing. And this is really an appetizer. We're going to work a bit more in the coming days and weeks on some of the theory behind this, but we wanted to really give you a good showcase of passive ocean color in particular through the decades. So you might have seen this image, hopefully. Maybe there's some of you who haven't. This was taken by astronaut Bill Anders in 1968. And I think this, in some ways, you could say is the birth of passive ocean color, perhaps, because it's a photograph. We live on a beautiful blue world, and that's what we learned from this. And it was really phenomenal. Years later, a decade later, NASA launched the Coastal Zone Color Scanner as a proof of concept radiometer that gave us these beautiful images of, our Earth and ocean environment. And really, for the first time, we could see incredible connections and synergies between the physics of the ocean and the ocean color, which we know is the biology and the non-biology that's influencing these things. It drew a lot of attention, including Tom York, great song. And really, it opened up a new era of observation. And so, of course, before satellite ocean color, we're working on ships, which is a great time, but also ships travel on average the speed of a bicycle. And so, if you really want synoptic views and to be able to characterize Earth as a system, satellites help beautifully. And we put up this quote by Walter Munk that Ivana shared with us that if he were to choose a single phrase to characterize the first century of oceanography, it would be a century of understatement. And so now with satellites, we have this beautiful way of in mostly unbiased view of our Earth from space.
Yeah, and I think we've talked a lot in this class already about being data limited and some of the challenges, even now that we have these tools, but it's pretty cool to think back to before we ever had that view of the ocean and understand that in a lot of ways we're quite lucky to have the access that we have and the understanding that we've been able to glean from that.
And a nearly unbroken time series, at least with SeaWiFS. So this is not new, but again, we had really profound discoveries with ocean color, allowing us to see Earth as an integrated system, which means that, again, with the launch of the Coastal Zone Color Scanner in the 70s, before then, people really thought of the ocean as a desert. And I think that's also obvious if you think about back when you were in grade school and you look at those maps of topography on Earth and the ocean is just flat blue and kind of boring and pale, and land gets all of these beautiful icy whites and these dark green colors. But now, we have a way and then a way to quantify that the production in the ocean is roughly equivalent to that on land. And that was a really profound discovery that, of course, has spurred so much since.
Yeah, and I feel like some of what we've, again, kind of primed you for is talking about like, oh, going beyond chlorophyll, but there's so much we can do with chlorophyll, right? So understanding this seasonal cycle and this time series through the time that we've had these observations, we still can say tremendous things about the Earth system that we were never able to say before.
So we wanted to hear from you if you have used satellites in your work or if you haven't, why you would want to use satellites and what sort of science questions you can answer with satellite information that you might not be able to from a ship or in situ buoy work, etc.
Just you can shout out an example. You gave examples almost every day of this class. You've all been thinking of one, but let's just, give us one. Go for it.
Spatial pattern and function. We have research on that one point, so we understand data.
Yeah, perfect. Getting that spatial context. Yeah, Tom.
And the temporal context too, because you can only go out so often.
Yeah, absolutely. Fantastic. Great. And you have your point samples within that context. Sure. Yeah.
Combining those two so you can kind of see trend, you can make a seasonality and then you can see anomalies from that and then understand those anomalies and context that you wouldn't have without satellite instruments.
Totally. Awesome. Yeah, go for it, Brittany.
A lot of satellite data is easily accessible and pretty.
Nice. Yeah, really good. Really good point. Yeah, Eva.
So many places of the world are really undersampled. Like it's so hard to get to like the Antarctic, for instance, or like Point Nemo, the middle of nowhere,
Right.
So if you have a satellite, it's collecting routine measurements of that without sending them.
Beautiful.
Totally. Yeah, perfect answers.
We can go back to the time that we did not sample.
Yes. Yeah, right.
Yeah.
If you're seeing something and you want to know if it happened the year before that, right? You can look in that data record, even if you weren't there and sampling yourself. Great point. Yeah,
Looking
Becca.
at like using satellite chlorophyll data for like MPCP model baselining and calibration validation.
Yeah.
Perfect. Awesome.
Great
Great.
answer.
Yeah, you're all on the right page. You know why
Yeah.
this is important. But just thinking about all these different scales with which we can bring these measurements together. And so why are we focusing on the satellite piece of it? This is how we wanted to get you thinking as you go into this next phase of the class.
Okay, so what would you say is remote sensing if somebody were to ask you? In its simplest case.
It's a term we use all the time, but what does it mean? You don't have to overthink it. Whatever comes to your mind is a way to
Right.
describe it.
Okay. Yeah,
Nice. Okay, awesome.
beautiful.
That's actually what the dictionary says. So I literally looked to see what the dictionary definition of remote sensing is, and they say the acquiring of information from a distance. And so then it kind of makes you think like, am I doing remote sensing right now, looking out at all of you, acquiring information about like what color your shirt is or what color your hair is with my eyes? By this definition, perhaps. So if we could get a little bit more specific, this is NASA's definition of remote sensing, which I think gives us some important parameters, but we might have ways that we want to think about if these are actually limiting us now that we've narrowed the scope. So the scanning of the Earth by a satellite or high-flying aircraft in order to obtain information about it. The piece that I really like from this is the obtain information about it, right? Because it's giving you a purpose and a goal in your method. But I think when we think more about the vast diversity of methods out there and the reasons that we might be doing this type of sampling or measuring, maybe things like satellite or high flying aircraft, right? We might need to give those definitions a little bit more room for how we're defining high flying. Does that just mean above your target? What's an aircraft? Is it a plane? Is it a drone? And then the scanning of the Earth, that's our focus in this class, but we talked yesterday about extraterrestrial oceans, right? And there's tons of opportunities there to use similar methods and approaches to think about maybe beyond our planet. So finding a way in which all of these pieces of information about the actual definition of remote sensing, what is your version of remote sensing? What are you doing and how would you define it? We also have a great example from your instructor, Dr. Bisson here, when she took the optics class.
Yeah, so you know, in this case, it was really can be as simple as an iPhone that's on a fishing pole. And we went out, this is Dr. Kale and Dr. Lambert. We went out in 2015 as a side project. And I would mention that the energy I'm feeling from this group is incredible. And so I totally see that happening again this year. We took images again with an iPhone strapped with duct tape. Eventually we used pipe and not a fishing rod, but we tried a number of things. We bought a $2 app that took photos at a regular interval. And then we image processed these little tidal ponds to quantify the fractal dimension as it relates to the Arctic. And we published it. So you can do a lot of really cool work with really frugal tools. And also, if you go to the next slide, you can do a lot of really cool work with very expensive tools. And so there's quite a range, of course, in what remote sensing offers.
Yeah, absolutely. And a piece of this clearly on both sides is creativity. What do you need? What capabilities do you need from your sensor? How are you going to answer the question you're asking? How do you need to put those two things together? So since you're getting a broad background in remote sensing as part of this course, maybe you've taken a class generally about remote sensing before, but we just wanted to walk through kind of some basic terms that you will hear about as you're thinking through these questions, maybe reading some of the basic literature. And these are things that are maybe a little bit more interchangeable between terrestrial and marine and aquatic remote sensing. So there are so many different approaches that you all are learning. You're all in very different grad environments where you maybe have like different course offerings available to you. And while you're digging really deeply into marine and aquatic remote sensing here, there's just some similarity that we can kind of all get on the same page as we're thinking about these terms. So for remote sensing, we need some type of light source. In this example that we're looking at, that's coming from the sun, but that's not always the case. We'll get into that more. And then you have some type of radiation from your light source that's hitting an object of interest, or maybe you want to call it a target. That's kind of more up to you. And as that light and your object interact, then you're going to get some reflected light. And so, you know, you just got to go through this in really good depth with Andrew, but we're giving you the 35,000 foot view of this. You can use these terms more interchangeably as you're thinking about things, but in your case, your object of interest is going to be a water body, and the things that you're trying to seek within that are going to have a signal in the reflected light, which will then be detected by your sensor, sending information to a receptor. Sometimes there are multiple receptors and required to get that information to you. And so when you're doing all of this data analysis and interpretation, you're kind of taking all of this path of light through the system to the sensor into account as part of your analysis that actually lets you say what you're seeing and why it's important. A big distinction that we wanted to just highlight right now, you're going to learn about both types of remote sensing in this class. So we have both passive and active types of remote sensing. This, I have no idea what the reef resilience network is, but we loved this diagram because it really gives you a nice sense of if you're doing remote sensing, you have your light source hitting kind of all these different pieces of the system, and maybe part of your challenge is narrowing down your information. So in this passive type of remote sensing, you have an external source of radiation, in this case, the sun. Pretty much, I don't know, does anyone know of a case where it wouldn't be the sun?
People do some measurements as a function of moonlight.
Okay.
Some paper, not paper.
Yeah.
Yes, I think they still said.
I don't know, Barney Balch's paper might not be younger than us, but yeah. Yeah. What is moonlight if not reflected sunlight off the moon? Yeah, Tom.
It's a microwave as well.
Oh, cool. Okay. Yeah. Right. So thinking about different wavelengths than the visible. Love it. Awesome. Right. And so this, again, you have multiple different sensors, but you have one source. And then I'll maybe pass it over to Kelsey to say a little bit more about active sensors.
Yeah, so active in contrast, it's active because it emits a signal and that signal then is returned to the sensor. So an example we'll talk about tomorrow is LiDAR. It has a light pulse with a known wavelength and energy, and really simply it produces photons that, hit the target or object of interest. It comes back and then you get information about where or what type that object is. So it's often these tend to be a bit more power intensive and a bit more expensive to develop, and it's an area of growth.
Yeah, right. And so then thinking about kind of all those different ways that you can be using a high flying aircraft or a satellite, all these different possible sensors, there are going to be so many different ways that you're measuring. And the things that you're measuring will be different depending on what your sensor is and where in your environment it is. So this was just trying to give an example of kind of some of these many ways that we have remote sensing going on all around us, even beyond the ways that we're maybe thinking about for our direct data collection and data analysis for our scientific purposes. Yeah.
Okay. Oh, this one we can click through slowly.
Yeah.
This is, it's a recap of really putting in an animation what we've been talking about in math. And so, the sun produces photons. They enter. Can you click again? And so, a large fraction of those will be absorbed. A small amount will be scattered back. And they scatter back to the receptor, which it often can be your eyes, and then often can be, again, a larger scale. So, as a review, and we have from this, incredibly accurate nanometer scale perception of the ocean, and often, of course, we know this, higher degree of sensitivity than our own eyes to distinguish. But we also have really good radiometers built in biologically. You can go to the next slide. And, as we talked about developing intuition, we also have intuition about a water body when we look at it. I know, like Gary, for example, you learn when you're a kid when it can be maybe healthier to swim there and when not by looking at the water. And so these are things that, again, you can think of with remote sensing, and you can see here, examples of what the spectrum might look like across these different water types. And we build algorithms, which will be, a topic of more focused lecture later on, but really, a lot of these are empirically derived, which is important to note, and depend upon, again, the degree of that we can sample the ocean well across a dynamic range. And from that, we can produce parameters of interest that allow us to enable a ton of science questions and really cool insights.
Yeah, this idea of using your eyes like a radiometer, it's a really fun one. And I think the intuition that you're all building in this class, like all the time you spent yesterday with Hydrolite, the measurements you're going to make in lab today, the more and more of this data that you look at and the different ocean conditions you look at and then process your radiometry data, try to understand how that matches to a specific color that you're seeing, you'll just get better and better at being able to look at a water body and try to maybe guess what the reflectance spectrum would look like. Or if you're at the beach, your friends are never going to know peace again, right? You're going to be looking at the water like, ooh, lots of scattering particles in there today. That's pretty cool. Oh, there's something that's absorbing. The water's kind of brown today. And people are going to kind of be like, okay, enough, like, forget it. But it's a really cool skill to have because you can gain a lot of intuition about the ocean just by looking at the water.
Beautifully said. And, we've invested as a country, which I think is one of the most beautiful things about country and other countries around the world through taxpayer dollars, you know, satellites that really fill in gaps of things that commercial sectors don't have an interest in. And so enabling these synoptic views at scales to really help us understand our world better. And so this is just an animation of that going back again to Nimbus 7, which carried the coastal zone color scanner we talked about at the beginning. And we have a beautiful vortex with many beautiful missions planned. Stay tuned. And I'll talk about one tomorrow that's in the LiDAR realm as well that's not on here.
Awesome. So yeah, as we have all these satellites and remote sensors up here, what are some of the considerations that we might be thinking about as we're putting together a remote sensing sensor satellite? We gave you some things to start thinking about here, and some of these are directly related to why you all were saying it's important to use these methods already, right? Your spatial resolution, your temporal coverage that you're getting, and your spectral resolution and signal strength are things that we've been talking about for the past whole week, even when we were just thinking about our inherent optical properties, right? Those wavelengths that you're measuring at, the features that you're trying to target, how high resolution does your information need to be in order to get the signal that you need? And then based on the question that you're asking, do you have enough signal in your system? In those spectra that you were showing us this morning from Hydrolight, right? Like in a system where your bottom reflectance is really impacting the other property that you want to derive in the optical signal, how much signal do you need to differentiate the thing that you're hoping to measure from your really reflective bottom and every other question that you're looking at within that?
Yeah, so the basics, this is a really simple view, but you know, hyperspectral, we get everything. Multispectral, you have these discrete bands that are limited, you know, and then monochromatic, which is what you'll see tomorrow with the LiDAR lecture. One wavelength, you know, you might think, what the heck could I do with one wavelength? Turns out a lot, but not nearly as much as you might be able to do with hyperspectral. And again, it really depends on the question. And so scientists have been informing satellite advancements, just as satellite advancements can inform science. So it really is this beautiful synergy, you know, that happens. And when I was taking this class, we had the instructors who were part of developing the PACE mission. And obviously you have that here in the room as well. And so that will likely and hopefully be your future too. So it's really important to think about, what do we want to know about our ocean? And then how do we design a sensor to get us there? And there are always trade-offs. So you can think here, you know, for example, thinking about PACE and wanting to or any satellite wanting to distinguish across different types. If you only had, for example, one wavelength, where would you want to have that wavelength in order to be able to discriminate? What if you have multispectral versus hyperspectral? So I think it's important to keep in mind, again, when thinking about all of these things, where what you have to work with, what it enables, and also what it limits.
Oh yeah, Sully, go for it.
Well, on the slide one before, but is active remote sensing like associated with one of these?
LiDAR right now is at what we have available from satellite at 532 and 1064 nanometers. There are goals. There's like a splitter, so basically you can do a factor of 2 in the way that the signal is distributed. And we're hoping to eventually have a blue LiDAR that's out there, but we don't have the technology yet to develop a multispectral in space.
Cool.
But in general, you can have active sensors that exist across, you know, numbers. So it's not necessarily like one or the other. It's a lot easier and cheaper to do multispectral or hyperspectral or passive.
Nice.
Because you're developing only a detector. And when you're doing LiDAR, you develop a laser. It goes all the way through the atmosphere. And you have to count what all that loss of light in the atmosphere, then bounces off, for example, from the ocean, then the secondary loss through the atmosphere. So it has to be really, really strong, but then you also don't want to burn people around. I mean, there's all these things to count for, but the energy, you know, it's pretty much, you know, you have to put it inside the amount of energy that sun is giving to, you know, project that color for stronger.
Really good question though. Yeah.
And we'll do a lab tomorrow that might help build intuition to retrieve photons by sending, for example, 10,000 photons down to Earth, and how many do you get back, and how big would your telescope size need to be? So that, I think, keep that in mind for tomorrow as well.
Awesome.
Probably a lot of you have worked with differing spatial resolution. And again, you know, we probably say, yeah, of course we want A, but there are times when, you know, C can be more computationally easier to do. It might be more appropriate for the types of questions that are being asked. So again, there's this trade-off space and what sort of spatial resolution of interest that you want and what tool could be best for it.
Yeah, Tom.
This might not be the time, but like at some point, are we gonna talk about super resolution and like the the thought behind whether or not that should ever be the case in ocean color.
I'll just get some friends in my machine learning.
Nice,
One
awesome.
day is one.
Yeah, and I think Jeremy's also planning to talk a bit about kind of trade-offs in designing a sensor and like,
Trade-offs.
Yeah.
Basically do a little exercise.
yeah, so yes is the answer. Now's the time to tell you yes.
Amazing. And so again, you can think about these different scales of variance or scales of influence in the ocean and what sensors is appropriate.
This is, if you're interested in what you're seeing on this slide, you might want to ask Patrick more about it because this is a really cool example of putting together a lot of different spatial scales and then thinking about how that variance changes based on your scale and your method.
Last three, you'll see on that 2 slides ago, I said normalized absorptions, it got published, but that was before I. took
On this
the
one?
class.
Oh, wow.
Oh, yeah, I did.
Wait, what a good self call out. I love that.
Good.
Nice. All right, for next time we'll put a little, yeah. But thank you for publicly acknowledging that we all make mistakes. It's important to see. Cool. So as we're thinking about designing our ideal satellite sensor and kind of some ways that we're optimizing our sampling based on our question, we wanted to just show you some examples of different types of orbits, especially if we're thinking about global scale remote sensing questions. This is kind of just like a very basic cartoon example. We'll show you some actual satellite sensors that are measuring in each of these different ways. But broadly, we have this example of geostationary orbit. This word might be familiar to many of you, but you can kind of infer from the name that you're looking at one place and over time, the satellite is monitoring in a consistent location, as opposed to this polar orbit where you're getting over a different time scale measurements of the entire globe, but with some gaps and some repeat coverage. So thinking about how you can optimize your sampling to relate to your question. And again, that kind of trade-offs question when you're designing a satellite sensor, what's your resolution? What's your frequency? How often do you need to be observing your system in order to get the information that you most need? Oh, sorry. Let's see if we can make this work. So yeah, just looking at an example from PACE where we're thinking about how that path is actually being traced around the globe based on the different instruments that are part of that whole package. And you're going to have different swaths and different amounts of coverage from the different instruments, and then also different repeat frequency as you're going around the entire globe. Some areas will end up getting a little bit more coverage, some areas will get a little bit less coverage, and you can make your global composite by averaging over that time that it takes to cover the entire globe as much as possible. Yeah, any of you who have used this type of data are familiar with the fact that you have both different spatial resolution and temporal resolution, and you have to choose the right product for the job. We also just had this example, which, you know, if you haven't ever looked at the NASA Scientific Visualization Studio, they make some really wonderful animations. So for you thinking about communicating your information, or for teaching this to all the people back in your lab at home, or for other, you know, opportunities that you have to share the magic of satellites, there's some great opportunities to show off these different types of remote sensing. This one's pretty chaotic.
Yeah, and we'll talk about this also a little bit later today, but throughout the class, and I think we are changing a little bit as a culture where it was maybe more common a few decades ago to be trained in one type of technique or one satellite and use that for a career. I think more often now we have so many incredible tools in space that can be used in tandem to really advance our understanding. And so I think at the moment NASA's flying 36 or so satellites that are Earth science centered in some way. And most of them, of course, are not optimized or intended for ocean use, but that does not mean we can use them, you know, and some of our really exciting discoveries more recently have come from taking sensors that were not designed for ocean use into an ocean realm. So this is just an advertisement for that.
Yeah, absolutely. And then thinking about as you're maximizing your signal from your satellite data, trying to target your question, this idea of how a satellite is sampling is going to really come into play, right? So if you look at all these different possible processes that you might hope to observe with remote sensing, there's some where it might be sufficient to get that polar satellite view where you're getting kind of this longer term view. But do you see any examples here where you'd really want more continuous coverage and would maybe aim for that kind of geostationary approach? Seeing some nodding. Maybe call them out. Which ones would you want geostationary satellites for?
Daily cycles.
Daily cycles, awesome. Yeah. So within here, some daily cycles. Yeah.
Oh, tidal sequences.
Yeah, exactly. Awesome. Perfect. Yeah.
Routine water quality monitoring.
Nice. Yeah, absolutely. Right. Even things that aren't totally on here. Yeah, awesome. So yeah, we were thinking kind of this side of the diagram is like just good examples of processes that you might need that daily and even throughout the day observations. And so you might sacrifice some other pieces, like you're going to be looking at a limited geographic range, but you can get really high temporal resolution information about that geographic range. Did you want to talk about this?
Oh, sure.
Specific example?
Because we love showing the pretty photos. But you really get a sense here, these are goes east and west, and you won't see the whole globe, but you can answer some really fundamental and very applied questions about how the ocean's changing on hourly scales, which is tremendous. And stay tuned for
Sorry.
Glimmer. Yep.
Oh, yeah,
No, it's
Glimmer.
just not pictured, but we'll be in the Gulf of Mexico area. So also another consideration, signal strength relative to noise. And so there are certain questions that we have as scientists where we really want to make sure that, a parameter is addressed to, let's say, 5% uncertainty. Some might be fine to be addressed within 40% uncertainty, right? Like we always want things as best as possible, but there are sometimes concessions, and some variables and scale of variability may not be as large where you can answer things differently. So this is another cartoon, pretty shittily done by me in PowerPoint one of these days, and just to give you a sense for things. I'll talk tomorrow and you'll see an example of this that you can look forward to, and it does make things really challenging with data processing and trusting the data. But again, that's sometimes where the fun happens, when you can pull information out from these really tricky spots.
Your Cisco secure client is
Oh,
asking
geez,
you
that's
here.
okay.
Okay, all right. I'm just gonna exit out. No, it's all good.
We're good on opposite.
Okay,
Go
cool.
next slide.
Awesome. Okay, there we go.
Okay, so again, I think Jeremy's giving this lecture soon, and Andrew also did a beautiful job talking about it again today, but we are with remote sensing working with an inverse problem. I should say passive remote sensing. And what that means is, the image, the direct data product that we get is not ultimately what we want. We might care about chlorophyll or suspended sediment, phytoplankton communities, and we're getting top of the atmosphere reflectance. So because of that, there are many more parameters we want to derive from the parameter that we have, which makes it an ill-posed problem, but one that can be solved using inversion algorithms. So often ancillary data or ancillary information in the form of empirically derived, fits or Bayesian type work can help with this. You can go to the next slide. So we've talked about this already, but basically, remote sensing reflectance is the ratio of the upwelling radiance to the downwelling irradiance. And there are some constants that have been known to a degree of high fidelity. And then you ultimately look at this relationship that's essentially backscattering divided by the sum of total absorption and backscattering. And to separate those components, we need to, create these basic functions that allow us to have a good sense for what they might look like, and often are a function of chlorophyll, for example, which you'll see more in the lab. But we wanted to expose to this again. Redundancy is the spice of life. And when Jeremy gets his lecture in more detail and you play with these, you'll get a sense and more intuition on how we can develop them further.
Yeah, we kind of talked about this problem a little bit on Monday when I brought up this concept to you that it's a physical problem, but we have a complex system, including the complexity of the biology, right? So this idea that Kelsey had on that previous slide of using ancillary data to eliminate these solutions that might solve the inverse problem, but don't actually make sense on Earth is really important.
And it is one equation to unknowns if you look from the simplification up there. And so you might remember from math, that's not an ideal place to be. So that's where we need help from you, from existing work, and maybe ancillary data. And so Ivana put this together 2 years ago. I really, really love this chart. I think it shows how our fundamental product, the top of the atmosphere radiance, propagates down all the way to a lot of the aspects that we care about, keeping in mind that with each derivation, we add in another layer of uncertainty and error. And so as you get further away from that TOA value, you add uncertainty to the problem. And as we improve, again, both our models at these intermediate stages, but then also the basic radiometric uncertainty at the top, we have, new capabilities to answer questions that maybe weren't previously answerable, which you'll see in your lifetime and is really exciting, I think, as a scientist.
Totally.
And within that also, again, you have one chief product, remote sensing reflectance, and see how many things we're deriving from it. So you can imagine there is a high degree of correlation between some of these. And one of the, critical areas is being able to understand that separation. And so there's been some work done in this area to really think about, and PCA, principal components analysis, is one way that one could tackle this problem, to look at how much, information statistically is contained in spectra, and what that looks like when you compare across components and how many you can retrieve. And so this is a scrape plot comparing the percent variance explained on the y-axis against the components from the PCA on the x-axis. And you're looking at this is an example with CWIFs, and we compared the products, which are in that sort of maroon line, with the reflectance. And again, it shows this high degree of correlation. And so, one way forward with inversions, which hasn't been done yet, so it's an open project if anyone wants, is to think, for example, about deriving a product from RRS, like chlorophyll, and then taking all the anomalies of that, basically the extra remaining information, and then using that to derive, rather than simultaneously deriving 10 products from one spectra, for example. And that would be something that'd be interesting to test.
Yeah, absolutely. We wanted to show you an example here of combining multiple different satellite sensors. Yeah, I see some woo-hoo. Awesome. That's how we feel about this too. So as we're on this kind of exciting time in scientific discovery where we have new sensors that are allowing us to see the ocean in new and different ways, those sensors are observing the same thing at the same time, right? So how can we put some of that information together to give us different information about different parts of the ocean that then will let us understand more of the ocean than we could with just one of these sensors or before either of them existed? So we talked the other day about the Moana algorithm when we were looking at phytoplankton community composition, and I kind of walked through with you an example of applying that to the whole Atlantic Ocean. But now we can see an example of really zooming in, and maybe we'll run through this animation one more time just so you can see it. If we're combining PACE to give us ocean color and SWOT to give us sea surface height, tell us in really, really high spatial resolution about the physical structure of the water that we're looking at, and how the PACE ocean color relates to this physical structure, then we can start to get some super interesting information about how these properties are all interrelated and how we might be able to make a model before we had PACE that tells us chlorophyll to these other communities. But with PACE, we can actually use that spectral information to relate the different communities that we're finding to the information we have from SWOT. So this is, I can't believe this, right? When I was taking the optics class, it didn't feel like it was that long ago, but we didn't have either of these sensors. And you all have this data. And as Brittany pointed out, it's pretty easy to access relative to a lot of different types of scientific data, and it's free. So if you can look at something like this and start to think about the questions you would ask by putting these sensors together, how can you really maximize as much information from remote sensing as possible by combining sensors that have different goals and maybe then have different spatial or temporal resolutions to help you answer your question?
Yeah, beautifully said. And I think within that concept of linking satellites together, sometimes we have the data and how can we make it work for us? And within those, those lines, we can also think about what do we know about the ocean and how do we make that connection? And so, remote sensing algorithms are often treating a pixel as independent from the other one, for example. But with this additional information, you could say, what happened to the water mass before it arrived here and what that might imply, or how could that even inform the satellite measurement? So again, it's bidirectional, I guess is what I'm saying.
Totally.
And we wanted to highlight again some of the exciting discoveries that, as we saw them within passive ocean color, where remote sensing, of course, has opened up so much. And these are areas I think that did profoundly change our community beyond the remote sensing community and into oceanography as a whole.
Yeah, when we were all talking about this last night, there was sort of this idea of like, oh, when you write the introduction to a paper, you have these kind of big concept things that have been discovered in our field using remote sensing, right? And so the time period in which those have been discovered and the way that we all just now assume they're facts that we all know, right? Like primary production in the ocean, super important. That wasn't something that we had an estimate of before we were able to have global ocean color. So just wanted to walk through quickly, give you a couple of fun examples and get you thinking about where we're going from here.
Yeah. So, another one that we love and has a lot of relevance to PACE and the current moment is thinking about, wildfire plumes and these more recent anthropogenic pressures that we're observing in our lifetime, and sensors that can not only quantify the ocean component, but also have really good resolution of the aerosol activity as well.
Totally.
We love kelp, and we know there's some kelp fans in the audience, but being able to observe kelp dynamics and how that changes also is something that is difficult but doable in situ. But again, with the synoptic view, you can say so much more. Similarly, with the synoptic view, you can start, and the time series view, when you have these long unbroken time series, you can answer questions about climate change, for example, which was previously not necessarily considered doable by satellite information.
Thinking about other targets that we might want to identify in the ocean, these kind of like end member things. I don't know about all of you, but when I talk about ocean color remote sensing and explain it to people in my life who aren't in the marine science world, one of the first questions I get is like, can you see trash with that? Can you see garbage in the ocean? Can you see the Great Pacific Garbage Patch, right? And so thinking about things like marine debris, whatever that means, along this spectrum of microplastics to larger floating debris, how can you use remote sensing data to really revolutionize those observations? We talked about this paper a bit on Monday, but the recent work coming out of Kath's lab looking at detection of copepods, so living particles that are larger than phytoplankton. What other things in the ocean have this biological signal that we can distinguish using ocean color remote sensing on enormous scales?
And similarly, thinking about land to sea continuum, this is one of the areas of the most dynamic biogeochemical exchange, and it has massive implications for these coastal communities and really all of us. And so that's something that we can quantify and work on from satellites as well.
Yeah, definitely. And then thinking about what about if the bottom reflectance is the signal, right? We were talking this morning about like, oh, you need to understand it so you can throw it out. But what if you want to understand it so you can survey it and understand where these different things are and how they're distributed and how they're changing? These massive carbon sinks or pools that we have, like seagrasses, right? Or mangroves. There are all these applications for coastal remote sensing where we actually want to make sure that we understand the water signal so that we can understand the things that are either right under the water or growing in the water as well. And what's next? It's you all are the future. You're going to decide what type of cool things we look at next and where the opportunities are. And when we're standing up here and chatting and you're saying in your head like, oh, I wonder about, or like, what if there's a gap, or has anybody tried to pursue all those ideas at some point? Write them down while you're here and follow them up later.
Yeah, and to that note, not only will you be, creating groundbreaking research, but then also we need to think about a world in which we will be seeing tipping points and we'll be seeing peak CO2 levels that we haven't since humanity has been around, right? And so we also need to think about how do you design a sensor when you can't predict the future, and what can you anticipate that will be there? And so this is it's hugely significant time for all of us in science, as we know, and we'll talk a lot about that. But I think in particular, in a climatic sense, it's a really profound time to be working in the oceanoptics field and also thinking about sensor design for decades to come.
Absolutely.
And so we don't end on tipping points that feel scary. We live in a beautiful watery world. And last year was NASA's Year of the Ocean, which was great, and put together this a number of graphics. So again, the Science Visualization Studio, and we can put that in the link context, is a good place to go with that. And
yeah,
so important to continue to feel excited about this and have the fun in it, as well as recognize the significance.
Yeah, we're right in the middle of the UN Ocean Decade, right? So you're halfway through the decade. We got to keep that push toward understanding our ocean going. And it's 12:01, so it's pretty much lunchtime.
No